Welcome to the 11th episode, which is number 10. Today, I'm going to take whatever this is, and whatever this is implementing a monoid on vectors of fixed size, and I'm going to do it in Idris. And this is a very good way to showcase where dependent types can prove themselves useful, because now I can simply tell the compiler, this is my vector, it has size 3, and everything that doesn't have size 3 will not be compatible with it. So all the rest also has to have size 3 when I'm interfacing with it, especially if I'm saying, well, addition with vectors, there's this thing where you have this thing of one size and this other thing of the other size. They have to be exactly the same ones, otherwise it makes no sense. And we can even extend that to have matrices and matrix multiplication, because the law in matrices, the way you compose matrices, that the I forgot if it's the row or the column, but like the output dimension of the matrix has to match the input dimension of the matrix adjacent to it. And that's how you multiply matrices. You like the interface between them has to be the same. I guess it depends if you write them row and column or column and row. In our case, it doesn't even matter, because it's really this question of, does the output match the input? Alrighty. Right, so the thing we need to say is the same as last week. It's, I have a vector here, 1, 2, 3. It is a vector of size 3 of integers, right? And it has to be only compatible with other vectors of size 3. And when I say compatible, it's going to be in the sense that if we do plus on them, then you add those two, then you put the result here, that's 5. Then you add those two, do plus, and that's 7. And then you do those two, you do plus, and that's 9. And that in general, like composing and putting vectors together, work when they're the same size. Right, so let's get to it. No, I don't have clean. Oh, clear. Let's make our file. Let's call it vectors. Let's call this main. And I'm just going to import the vectors that are already in the language. And the reason for this is because I don't want to focus on how to implement that in Idris. This is more a Idris tutorial to understand how to implement vectors. We just want to use them. So let's go. The first thing to do is here we define monoid. Thankfully, it's already defined for us in the standard library. There is nothing for us to do. So as you can see, there is, it extends semigroup. And semigroup, you'll see, is, where is it? It's just this operator here with plus. And this operator is what puts two things together. So monoids is the thing that puts two things together plus the neutral element. The angle is not quite good. There we go. So it's operator and neutral element. And the operator comes from semigroup, which is the same as monoid, except it doesn't have neutral. All right, so we want to implement monoid on vector, right? And so for this, we need to, oh wait, oh, we have a problem. Oh, thank God it's not there. Cool. So I have to implement monoids on vectors, right? So we need to implement this. Left-hand side, right-hand side. And this is plus. And we want to implement neutral. But if we compile this, oops, what we will get is, and I'm gonna shut this up because it's really loud. It is complaining right now that we are expecting a type, but vectors is of this thing here, right? So if we look at vect, it says data type vect takes a length and an element type. So this is the length, this is the size of our list. So if we go here, it's this thing, and it takes an element type. So if you go back our Swift, it's that thing. So vectors defined by those two nested types. So we need to give it to the implementation, tell it, okay, it works with vectors, but it works with vectors of size n, which takes elements a. Is it not? I have to do that? Yeah. I have to define them separately. It's okay. So semigroup is the combining two vectors together, and neutral is what is the vector that's such that when you combine it with something else, nothing is special. So let's go back to our thing. So remember, with lists, we had something that said if you have a list of numbers like 1, 2, 3, if you combine it with another list like 4, 5, 6, then you get the list 1, 2, 3, 4, 5, 6, right? This is not what we want to do. This is absolutely not what we want to do. What we want to do is, if you have the vector 1, 2, 3 and the vector 4, 5, 6, then you get the vector of those things summed up. So 9, 7, 5. Right, this is the thing we want to do. It's different. So before, monoid and list was just concatenating them together. Now it means like stacking them, stacking each value pairwise, and doing the operation between them. Also, you notice that here, like we're doing an operation as well. So it's not just magically combining them. We also have to combine the elements within them. So I'm going to add a new constraint and say the elements themselves have to be semigroups. So the plus here comes from the semigroup of those values. Okay. Oh. Cool. All right, so we can already do this one, right? Because we know that, oh, never mind. Let's start with this one. So one great thing with Idris is that you can ask what is the type of something. So in Vim, if you use the Idris plugin, there is a shortcut. You can do \t, and then you have this nice helpful window here that tells you what is in context, what is it that you're looking at. So what we're looking at is a vector of size n. What is in context is the left-hand side of the operator and the right-hand side of the operator. And they're both vectors of size n. We also have access to the type, but it doesn't tell you anything about the type. And we also have access to the size of the vector. And we're going to have to use this size to do different things depending on the size. So the first thing we have to know is if the vector is empty, there is nothing to do. You're combining two vectors of empty sizes, so the remaining vector also has to be empty. That's the same thing as what we've done here. When we implement monoid on nil, right? You're adding an empty vector and another empty vector. There is nothing to do except returning the empty vector. So we're gonna do that. Compile. Actually, I can do that here. And ask again, what's up with that? So here we haven't, looks like we haven't made progress, but we already know that if we keep pattern matching, that is decomposing the vector, this is the cons case. And since both vectors are the same size, we know that in both cases we have an element and then the rest. So I'm going to put xs as the first vector and ys as the second vector. And look at the types again. And see here we know that well, it doesn't really say that, but it says that the remaining vectors, the nested vector, right? So if we look at here, here we have our nested vector. We know that those two values are the same, or rather, those two types are the same. The values of the size are the same. So that's what it means that xs and ys are of size len for length. And here, right there, it says the vector we have to return is of size s length, which means successor, which is what we've done here, right? We have to return a successor of whatever is the cons of whatever's here. Sorry, not successor, a cons, which means that this size is successor of the size of this one. So let's do it. What is the first value? So the first value is, since we know that those two are semigroups, well, that means we can do x operation y and then cons and then build the rest of the vector. So let's look at that. Now it just says plus, but since we've already done the first part, we can simply make a recursive call and say, oh, just figure the rest out. So just do that. And it's not happy. I think I know why. All right. So that's how to combine two vectors together, and we can already try this out now. So if we do 1, 2, 3, and then 4, 4, 5, 6. Oh no, it's not using the correct one. Use mine. Oh, I knew that would happen. Oh no, it's because it's using, okay. It's because it's thinking that those are lists. 3 and wait a second, does semigroup not? Jesus, semigroup is not implemented on integers. All right. That's going to be really easy. There we go. So now it's working. This is just a function that tells whatever the type here is going to be the type of this value. So here you give it a type, and then you give it a value of this type, and it's going to return the value of the type. It works because this can be overloaded as either a string, either a list or a vector. So we're going to tell it, in case you have to choose the vector one. And it works. So if we add 1, 2, 3, 4 to 4, 5, 6, 1, 2, 3 to 4, 5, 6, we get 5, 7, 9. And you can see that if I do that, it's complaining that the lengths here don't match. It's not entirely obvious which length doesn't match with which. Maybe if I do that. No. If I change that. Yeah, that's a bit better. So basically it went through all the addition here. And then at some point it looks at that and it says, okay, I'm going to decompose the first one because it's of size 4. So it's looking in the last element. And then it tries to decompose the other one, but it's of size 0 because it's only 3 elements. It's already gone through the 3 elements and now it's empty. And it's saying, well, I was expecting something of size at least 1 and I got something of size 0. And it is noteworthy to say that this is all at compile time. This is not while running the program. This is while compiling the program. And I can show that by doing this. So addition is just going to be a vect3 int. And that's going to be 1, 2, 3. And 4, 5, 6. Right, save. And we're going to compile this. Oh, does it check? Yeah. Oh, of course it works because those are the same size, right? However, now it's complaining, right? I'm not running the program, I'm just compiling the file, and it says, well, you said you had vectors of size 3, and here you have vector size 4, so that's not happening. Right, so we've already implemented all of this quite painlessly, actually, in a couple minutes, where this took us the entire session. Well, we haven't implemented vectors, but that's okay. So now the thing I want to show you is, oh, the neutral. Yeah, let's go with neutral. So let's make another function for this. So neutral vect. A neutral vect is a vector of size NA. Let's go back here. So neutral vect is the vector of size NA that is such that if you add it to another vector, it doesn't do anything. One thing I want to showcase is how Idris can automatically generate code for you. So if I do \d, it generates a skeleton definition for a function. And then here, what I have to do is, if I look at the Idris compiler, I can do search. Let me type search. I can search for function that have a predefined signature. So I'm looking for a signature that is given a natural number and a value, make me a vector of size n, which is filled with the same value. And so it tells me there is 3 functions that match this description. There is replicate, which is exactly what we want. Takes a length, takes an element, and returns a vector of the size length, which is filled with this one element. And then there is return in pure, which kind of match the shape, but don't match the exact types. So we're going to use replicate. And here, the thing we want to replicate is n, the size of the vector, right? We know it's of size n, so we're going to replicate n times. And then we're going to fill it with neutral values. But what kind of neutral values? Oh, okay, first of all, see the n here? The n is for the size of the vector. You can already see it here, right? This is the same n. We're saying, I want a vector of size n. Well, here it is. We have to bring it into scope first with this fancy syntax, and that works. And if I ask, I could also go here and say, what is the type of this hole that I haven't filled in? It says it's type A. So let me show you exactly what we want to do now. So we have rather neutral gives us a vector of neutral elements of the right size. So this, for example, would be the neutral for vectors of size 3, where the neutral element is n. If I say, for example, what is the neutral element for vector of size 2 of string, well, this is the vector that contains 2 empty strings. What is the neutral element for vectors of size 4 of ints, where combining them means adding them? Well, it's the vector with 4 zeros, right? And the reason is, if you add another vector of size 4, you get exactly the same vector back. So this means it must be the neutral element. So we already have replicate n, where n is the size of the vector. Now we need to get the neutral element of A. And for this, we're going to have as a constraint that A also has to be monoid, such that there is a neutral element. And there we go. So now I can just do here. Neutral vect. And it works. Cool. Just a sec. There we go. Oh, is it dead? No, it's all right. Oh, that's the wrong file. Okay, what time is it? 30 minutes. Good, good. We have plenty of time. The other thing I want to do is matrix multiplication. So let's go. Yeah. So a matrix is the same thing as a vector, except it has vectors inside of itself. So if I say, imagine I have a vector here, and it has 2 values. One of them is a vector of size 3. The other one is another vector of size 3. This is a matrix, and typically you write this. Actually, I should put this on the side. Typically, you write this as a table like this with parentheses on the sides, on each side. Oh. Can I move this thing away? Yeah, I can. And so matrix multiplication is a bit tricky because it involves a lot of operation, a lot of repeating operations. So if I do this matrix times this one, Well, what I have to do is take this, multiply them together. Now take this, multiply them together, and then add the results. And so, since matrices are just vectors of vectors, we can check and know in advance, the size of them. So let's define matrices by saying a matrix takes a height and a width as natural numbers and is simply a vector of height and then width. Oh, it takes an element type. Right. So if you draw this, actually I got this wrong. Boop. HWE. All right, this should compile. Almost. There we go. This is Andrew from the future, and I was editing the show number 10, but it was a bit of a catastrophe when I was going through it. So I'm doing it again as a video. So I've made some changes from before. Matrix will be defined as two vectors, width and height, but I want to flip those. So the first one will be height, the second one will be width. And the reason for this is just because I'm used to coordinate system where the first coordinate is the horizontal coordinate, and the second coordinate is the vertical one. And flipping them here makes the pattern matching a bit nicer. So what we want to do, the reason for this video at the beginning was we can prove not only that vectors have some sizes and that we can know the size at compile time, we can also do that with multiple vectors of vectors and have matrices that multiply together in a way that is sensible, where the width of one matrix matches the height of the second. So let's first begin with starting to implement whatever we want to do with matrices. So what we want to do is, given matrix AB and given matrix BC, we want to get matrix AC, right? This is the typical matrix multiplication. But in order to get there, we need to go through some intermediary steps. The first step is transpose. What is transpose? Transpose means that if this is a matrix, you do this operation, right? You flip it along its diagonal. Notice that the corner here and the corner here, they don't move, right? This one stays there, and this one stays where it is. And the opposite corner, they get flipped around. So this ends up here, right? And this ends up here, right? And the effect is really dramatic when you have, for example, one line, which is this like horizontal vector. When you do this, you get one column with the same amount of rows as you had columns before. Do 1, 2, 3 transpose, I will get 1, 2, 3 as a column. If I do 2, 3, 4, 5, and I transpose, the corners don't move, but the other elements get flipped around. And if I do 1, 2, 3, 4, 5, 6, every line becomes a column and every column becomes a line. So you get 1, 2, 3, 4, 5, 6. So you see how we've gone from one row to one column, one row to one column. Here we went from 2 rows to 2 columns, and 3 columns to 3 rows. So this is what it does. It just flips the thing around through the diagonal. If you write this down, you get matrix AB becomes matrix BA, right? Every line becomes a column and every column becomes a line. If we look at the definition that Idris gives us, we don't really go anywhere, right? We're just given BA and we have to get to AB, but we don't know how. So a good first step is to pattern match on the argument and see what is going on. So this means, since the first dimension is the height, as we can see here, so this is B, we see the height is 0, which means for the next thing, it must have width 0. But though the height is 0, the width isn't. This is a vector that has one of its dimension as empty. But if you flip it, the other dimension is not empty, but is full of vectors that are empty. So this is, for example, and this is an example where A is not empty, B is empty. Since we go from AB to BA, well, we have to make a vector of height A, but is full of B's that are zeros. So if we put a concrete number, this is matrix 3, 0, and we need to make matrix 0, 3. And so here you see we have to make a vector. Basically, we don't have a choice. We have to take the empty vector and repeat the empty vector 8 times. And for this, if you do search on the REPL and say you search for a function that takes a natural number, it takes an element, and it takes and returns a vector of the size of the number we told it to be, which is full of elements that we told it to be, we have this function called replicate, which takes len, length, takes an element, and returns a vector of that length, which is full of copies of this element. So we can just use replicate a empty vector. And actually I can just do that. Oh, and now it says no such variable A, right? A, remember, is the height of the vector. We have to get it, the width of the vector. We have to get it from the types of, to do that we do curly brackets. And this says take this value and bring it into scope. And now it's going to say that we need to fill it with empty vectors, and there is only one way to have empty vectors, and that's to put the empty vector. All right, and I'm going to do one more thing, is I'm going to call this transpose matrix. Oh, actually I should do it this way. I should do matrix transpose. And the reason is there is already a transpose function. All right. So now we need to go through the case where the dimensions are not empty, right? So if we ask what's going on here, we are given vector of, well, matrices len A, and we're given the first row, x. And we have to return something of length A, which has one additional row. So this is a bit complicated, but a good first step is to do a recursive call to solve the simpler cases and then look at what we're dealing with. So if I do matrix transpose of XS, what I have here is now T, which is a matrix of width A and height length. And I have XS and A. So the first thing to notice is this vector, and the goal, the return vector, all have the same size. This is a very good, starting point. And now the second thing to notice is this vector here contains rows of width len, of width len. And we need to append for each row, we need to put in front of it the new element that we're missing. Because this is actually so what it does is basically for each, this is every column. At every column, you have to add the new element that comes from the row from before, right? So you had a row, and you transpose it, and now it becomes a column, so you have to put it in front of the other rows. All right, so in order to do that, we have to somehow combine, I'm just gonna put it this way, combine X and T. And if I look at the whole combine, it's gonna tell me, well, you need a function that takes this vector, this other vector, and merge them into this. I haven't tested this. Does search give me anything? Search vect a int, vect a vect l int, vect a vect s of l a int. No, it doesn't. But that's fine. The only thing we need to do is actually very simple. We have a vector of int, and we have a vector of L, and every int here has to go in front of this vector. And there is a function for this. This is called zipWidth. So zipWidth takes two vectors of the same size and merge every element pairwise with a given function. If I take the iPad here, I have the vector 1, 2, 3, and 4, 5, 6. It's gonna take f, and it's gonna do f of 1 and 4, f of 2 and 3, and f of 3 and 6, and that will give us the vector f14, f25, f36. And if f is plus, well, you will get the vector 5, 7, and 9. So let's go with the zipWidth, and let's look at our combine function. And so the combine function is actually really simple. Is take an element, take a vector, and put it in front of it. Search, and there is only one. That's the cons constructor. So we can actually do that. Oh. Can't do that automatically, but close enough. Compile, and we're done. All right. Now there is another. So we're able to take a matrix and flip it over like this. There is another operation that we need to do, and this is you take two vectors and you merge them, not in a way that creates a new vector, but in a way that creates a new value. You extract, it's like you extract the essence of the vector into, like, or you summarize the relationship between those two vectors by merging them into a single value. So if I take the iPad again, if I have 1, 2, 3, and 4, 5, 6, and I want to do this merge, one thing I can do, and this is the thing we're going to do, is I can multiply every element pairwise and then do the sum, right? So I do 1 times 4, 2 times 3, and 3 times 6, and I save those results and then I add them together. So 1 times 4 is 5, 2 times 3 is 6, and 3 times 6 is 18. Actually, I'm not going to do that. Yeah, I'm going to do plus here. And so this is 5 plus 6 plus 18. 5 plus 6 plus 18 is 11 plus 18. That's 29, I think. Yes. And those multiplications are correct. Yes. And that's what we're going to do. So again, you can see here we're going to have to use the same thing that we used before. We're going to have to do an operation pairwise on each thing, and that will give us a vector, and then we're going to sum every element inside the vector. So let's call this the dot product by accident. And we take vector of size n and int, vector of size n and int, and return vector of size n int. And if we want to do the pairwise thing first, that's going to be zip width. And the operation is multiplication, right? We're going to multiply every element with the other that corresponds. And then we can ask what is going to go here. And here what we need to do is simply, oh, I messed up. Here, the function that we need is going to take a vector of integers and sum them to get a vector of integers. And I think there is a function for this. And it is called sum. It adds together all the elements of a structure. So let's do this. And we can actually try it now. So we have 1, 2, 3, and 4, 5, 6. So if I do dot product of 1, 2, 3, and 4, 5, 6, I get 32. How do I get 32? What? Oh, because I'm stupid. Okay. All right, I can't. Yeah, arithmetic is never going to work for me. So 1, oh my god. 1 times 4 is not 5. 1 times 4 is 4. 2 times 5 is not 6, it's 10. And then 3 times 6, this one is correct, is 18. Now if you sum this up, 10 plus 18 is 28, and 28 plus 4 is 32. There you have it. Oh, we haven't tried transpose. Okay, let's try transpose. Let's make a small matrix. Let's make 3 by 2 matrix 3, 2. So it's width 3 and height 2. Yeah. 1, 2, 3, 4, 5, 6. Compile. There we go. And now let's do 2 by 3, just so we can compare. And this is going to be, so this is width 2 and height 3. I'm going to go 0, 9, 8, 7, 6, 5. Compile. There we go. And now we do matrix transpose of 2 by 3. And so every line becomes a column, and every column becomes a line. So the first line should be 086, 086, yep. And the second should be 975, and it's 975. So those two work. So now we can finally get to matrix multiply. Matrix multiply is going to be quite tricky because there is a lot of things we need to notice. So if I look at the type, the first thing I want you to notice is this very, very, very interesting fact that the height of the second argument is the height of the result. So we don't have to change a lot if we go, like if our starting point is, if the starting point is the second argument, we just have to modify every row of the second argument to make it work. So let's go with this. Let's go with map, because map doesn't modify the amount of elements, it just modifies the element themselves. So map each row to something else. And the function that we need to do will transform a vector of size b into a vector of size a. Now, how do we do that? So that means every vector, every row has to become a new row which has this size, right? So I'm going to call this func, and I'm going to give it as first argument x, where x is the other matrix. I want to look at the other matrix because what I want to do is basically for every row, I need to pick the corresponding column of the other one, right? And then merge them to get the element that fits. So there is a shortcut for this. That's what I wanted, but oops. Oh, there we go. Does this work? Yeah. So I only need the first matrix. I don't need the second matrix. And here, I'm going to create a new skeleton and look at the definition. So this is not actually very helpful, right? Because we need to get the vector of the new size, but we're given the old size. But the good thing is here you see we have vector of size a, which is the same as this one. The problem is it's nested into this matrix BA. So if we flip the matrix, I'm going to do that here. Let's flipped matrix transpose XS. If we flip it, we're going to get, that's because M and row. I'm going to call this matrix and this row, and this is flip matrix. Right, if we flip the matrix, we get a matrix that has that is of height A and has rows of width B. So we need now to find a way to map this thing into a vector of size A. So it's going to be something like map and then flipped, right? And here's where the magic happens. So now we're going through every column of the left matrix. Like if I take my drawing again, we're mapping through every one of those elements. So the first element of the map will be this column, and then the second will be this, and then the third will be this. The only thing we need to do now is to multiply with whatever this row is. I have to do times row. And it turns out we already have the times row because the row is right here. So if we do dot product row, this means times the row. You multiply the row times the other column, and you're done. That's it. That's all there is. Like, that's literally it. There's nothing more to this. We magically finished. So if we reload and I do matrix multiply of 2 by 3 and 3 by 2, I get, well, I didn't get what I wanted, but it works. I wanted to do 3 by 2 times 2 by 3. There we go. That's a more interesting one. So you see the first element we computed correctly was 36. I haven't looked at the other ones. But now we can test this. So if I take a web browser and I go into Wolfram Alpha and I do whatever this is, so it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And it's times 0, 9, 8, 7, 6, 5. We should get the same thing. All right, I've done it in reverse order, but it's fine. We've done it too. So it's 34, 38, 76, and 101. And yep, here it is. So we intuitively managed to implement matrix multiply simply by looking at what are the types, what are the operations that we're allowed to do, and what kind of makes sense given the tools that we have. So we needed two things to get there. We need transposition, we need dot product, and then we need to notice those interesting tidbits about how the rows and how the column correspond to each other, and how we can flip them in order to make our life more, make our job easier. Yep. All right, that's it for today, and thanks for watching. See you later.